Hi, welcome to this lecture on priority queues. Here's the outline for this lecture. We'll first talk about the API for this data structure called a priority queue, and then we will discuss some basic implementation strategies of that API, and then we will talk about a data structure called Heap and discuss some algorithms on heaps, and then we'll talk about how you use those algorithms to implement the priority queue API. And then finally, we will talk about Heapsort, which is a sorting algorithm that you get almost for free once you have a priority queue in place. So let's start. Now, in many applications, we want to process items having keys in some order, but we don't necessarily want them in full sorted order, and we don't want them all at once. All right, so at any given time we are only interested in, for example, the maximum element, and then at a later time we might be interested in the second largest element, and so on and so on. So we don't want them all in sorted order at once. So a suitable data structure in such applications is the priority queue, or PQ for short. And a priority queue supports two fundamental operations, and those are insert and remove either the minimum or maximum, right? So two fundamental operations that a priority queue support are insert a key into the priority queue and remove the minimum or maximum from the priority queue. Now, depending on whether you're talking about removing the minimum or the maximum, we have two different APIs for the priority queue data structure. One called min-pq and the other called max-pq. So here what you're looking at is the API for the min-pq data structure. So you have a constructor that takes a certain capacity as an argument and constructs an a priority queue with the given initial capacity, right? So the priority queue is initially empty, but it has a capacity of that. There is another constructor that lets you build an empty priority queue, and then once you have a priority queue, you can check if it is empty or not using this method. You can ask for its size, which simply returns the number of keys in the priority queue. And then you can insert a generic key into the priority queue using this method. And then you can get the minimum key or the smallest key in the priority queue using this method. And you can use this method del-min to return and remove the smallest key in the priority queue. So this method not only gets you the smallest key in the priority queue, but it also removes it from the PQ. Okay. And then you have this iterator method with which you can iterate over the keys in the priority queue in ascending order. Since this is a min PQ, this iterator lets you iterate over the keys in ascending order. Okay. So that's the API for the min PQ data structure. Here's the API for the max PQ data structure. So here you can construct a max PQ with this given capacity. So this builds an empty PQ with the given capacity. You can use this constructor to construct an empty PQ. You can use this method to access the largest key in the priority queue. And this method returns and removes the largest key in the priority queue. And then this one here, this iterator method, returns an iterator with which you can iterate over the keys in the priority queue in descending order, right? And that is because this is a max PQ. Okay. So that's the API for the min PQ and max PQ data structures. Here is a very simple client program of the min PQ data structure. So what this program does is it receives a command line argument called m, and then it builds a min PQ object. So PQ is of type min PQ, and this min PQ is going to store transaction objects, right? And we are creating this priority queue with size m+1. And then what we are doing in this while loop is, from standard in, we read information one line at a time. And with that single line, what we do is build a transaction object. So transaction is an object of type transaction. And we build the transaction from a single line. And this line has information about the person involved in the transaction, the name of the person. And then it has information about the date of the transaction, and it has information about the transaction amount. So that's what each line contains, right? So we take that line and we build a transaction object from it, and then we simply insert that transaction object into the priority queue. Okay, and then what we do is we check if the size of the priority queue is greater than m, which was this command line argument, and if so, we remove the minimum transaction object from the priority queue. So we remove the minimum key, meaning we remove the smallest transaction. All right. Okay. So once the while loop is done, we have some transaction objects in it. All right. And we have precisely m transaction objects in it. And then what are we doing here? We create a stack object. It's a stack of transaction objects. And then what we do here is we simply iterate over the priority queue, right? So priority queue, remember, is an iterable data structure, so you can iterate over it. And each element is a transaction object, because that's how we set up our priority queue. And then we simply take that transaction object and insert it or push it into the stack. So once this for loop is done, the stack has the transaction objects from the priority queue. Okay. All right. Now there's something to notice here. When we go through the transaction objects in PQ, in what order are we iterating over them? Well, we are iterating over them in ascending order, because we are using a min PQ. Right? So the transactions are iterated over in ascending order. Well, ascending by what? That depends on how transaction is implemented, or to be more precise, that depends on how transaction was made comparable. So if you happen to look at the implementation of transaction, you will see that it is comparable by the transaction amount. Okay, so what we are doing here is simply iterating over the transaction objects in ascending order of amount of transaction. Okay. All right, and then we push those transaction objects onto a stack. So once this for loop is done, what is the topmost element on the stack? Well, it is a transaction object corresponding to the largest amount. All right, so if then you traverse the stack, or if you iterate over the stack and print out the transaction objects, those are going to come out in descending order. Okay. And that's because of the last in first out policy that the stack data structure implements. Okay, so we are simply iterating over the transaction objects in the stack, and they come out in descending order of amount. All right, so this program is called top m because we are printing the top m transactions. So let's look at some input and output. So here is a file called tinybatch.txt that contains transaction information. So this line is one transaction. It has the name of the person involved in the transaction. It has a date, and it has a transaction amount. And then you have another line with a name, date, and transaction amount, and so on and so on and so on. Now what we're going to do is take this file and feed it as standard input to the top m program. Right? So we run top m, giving it 5 as the command line argument, so that's m, and we feed this file as standard in to the program. And what are we asking for here? We are asking for the top 5 transactions in this file, and that's what the program prints. So there are 5 transactions, and notice that they are arranged in descending order of amount. Okay, so that's a nice program that shows how you work with this priority queue data structure. And in this particular case, we made use of the minpq API. All right. So now let's look at some basic implementation strategies of the priority queue API. And these basic strategies involve arrays or linked lists, right? So we can either use an array or a linked list, each ordered or unordered. All right. Now, but if you do that, if you either consider an ordered or unordered array or an ordered or unordered linked list, then you're going to have one of the operations, insert or remove the minimum or maximum, take linear time in the worst case. All right. So let's think about this carefully. What are the 2 basic operations that a priority queue allows? It is either insert or it is remove the minimum or maximum. Okay. So let's say we are talking about implementing the minpq API using an ordered array. So if it is an ordered array, then so minpq using ordered array. So in that case, what is the cost of inserting a key into an ordered array? Well, you need to find the right place for that key, right? With respect to the elements that are already in the array. So that operation is a linear time operation. All right. So you need to find the right place, and then once you find the place for it, you need to move the elements next to it to the right by 1. Okay, so that is a linear time operation. So insert in that case is linear. What about removing the minimum? Well, that's a constant time operation because the underlying array is ordered. So the smallest key is the very first element in the array. Okay, so what we are saying is that if you use an ordered array to implement a minpq, insert is linear, whereas remove the minimum is constant. What about using an unordered array? So minpq now using an unordered array. Well, in that case, insert becomes a constant time operation because it really doesn't matter. You can insert it right at the very end of the unordered array. So that's a constant time operation. But what about removing the minimum? Well, that's a linear time operation because you have to scan the array, the entire array, to find out the minimum key. Okay. So in that case, insert is a constant time operation, whereas remove the minimum is a linear time operation. And the same is also true with an implementation that uses a linked list. So let's think about that. So minpq using an ordered linked list. Well, here, what about the insert operation? Well, again, you have to find the right place for that key that you're trying to insert in the linked list. So that's a linear time operation. All right. But what about removing the minimum? Well, that's simply removing the first node in the linked list. So removing the minimum is a constant time operation. And what about an unordered linked list? Well, there you can simply insert the given key at the head of the linked list, so that's constant time operation. But what about removing the minimum? That takes a scan of that entire linked list, so that becomes a linear time operation, right? So what we are saying is that regardless of what you use, meaning whether you use an ordered or unordered array or an ordered or unordered linked list, one of these two operations is going to be inefficient. It's going to be a linear time operation, right? So the question is, can we do better? And the answer is yes, and we will be able to do that using a very specialized data structure called a heap. Okay, so the heap data structure that we're going to look at next will enable the implementation of the priority queue API, where both operations are guaranteed to be fast. By both operations, we mean insert or remove the minimum or maximum. Okay, remove the minimum in case of a min PQ data structure, and remove the maximum in the case of a max PQ data structure. So here is the table that shows the worst case running time for the different priority queue implementations. If you use an ordered array, then insert is linear, as we talked about, and remove the minimum or maximum is constant time. If we use an unordered array, insert is constant, whereas remove the minimum is a linear operation. In the case of an ordered linked list, insert is linear, but remove the minimum is constant. In the case of an unordered linked list, insert is constant, whereas remove the minimum is a linear time operation. And with heap, which is what we're going to use to implement the priority queue API, it turns out that both insert and remove the minimum or maximum are logarithmic operations, right? So that's very efficient. Now what is impossible is doing both insert and remove in constant time. So that's simply not possible. So the best that we can do is logarithmic for both insert and remove. And that's done using this data structure called a heap, which is what we're going to discuss next. So let's look at this heap data structure. So we'll first start with the concept of a binary tree. So what is a binary tree? Well, a binary tree is a tree data structure in which each node has at most 2 children. Okay, so a binary tree would look something like that. So each node has at most 2 children. Now, a maximum oriented heap ordered binary tree is a binary tree, which is what we just talked about, in which each node is larger than or equal to the keys in that node's 2 children, if any. Right? So what we're saying here is that a maximum oriented heap ordered binary tree is a binary tree which looks something like that. So the key here, for example, 7 is greater than or equal to the keys in its 2 children. So here, for example, we might have 3, we might have 4. So notice that 7 is greater than or equal to these 2 guys. And if these guys have children, then it might be something like 1. So 3 is again greater than 1. So that's what we are saying here. So a maximum oriented heap ordered binary tree is a binary tree in which each node is greater than or equal to the keys in that node's 2 children, right? So where do you then find the largest key in a maximum oriented heap ordered binary tree? Well, it is found at the root. Okay, so in such a tree, the largest key is going to be found at the root. Now, a binary key, a binary heap is a collection of keys that is arranged in a complete heap ordered binary tree, represented in level order in an array. Okay, not using the first entry. So what does it mean? What we are saying here is that a binary heap is simply represented as an array internally. All right. And here is the correspondence. So you have this binary tree, which is a heap ordered binary tree. Notice that every key is greater than or equal to its 2 children. All right. So T is greater than S. It is also greater than R. R is greater than O. R is also greater than A. S is greater than P, S is greater than N, P is greater than E, P is greater than I, N is greater than H, N is greater than G. So this is a maximum oriented heap ordered binary tree. The largest key is at the root, so that's the largest key. And how do we represent this internally? We're going to represent this as an array. All right. So in this case, so what is the correspondence between a node in the heap ordered binary tree and the array? Well, it is as follows. So this heap ordered binary tree has 11 elements. So we are going to use an array of size 12 to represent this heap ordered binary tree. We're going to ignore the 0th index. So you see a dash there. Okay. And then the root element whose index is 1 is the very first element in the array. It's at index 1 in the array. And then its two children whose indices are 2 and 3 are these elements S and R in the array with indices 2 and 3. All right. And then S's children whose indices are 4 and 5 in the tree are at indices 4 and 5 in the array, P and N. Okay. And the children of R, which are O and A with indices 6 and 7, are at indices 6 and 7 in the array, and so on and so on and so on. All right. So how do we assign these indices to nodes in the tree? Well, we start with 1 for the root, and then we simply go in level order. All right. So 1, 2, 3 for the two children of T, namely S and R, and then 4 and 5, 6 and 7 for the children of S and R, which are P, N, O, and A. And then the next level is 8, 9, 10, and 11 for the children of P and N. All right. Now, if you were to insert another element into this tree, that is going to end up right here. And its index is going to be 12. One more element, it's going to end up there with index 13. And then if you insert two more elements, they're going to go there with indices 14 and 15. All right. Okay. And these indices have a direct correspondence to indices in the array A. All right, which is the underlying representation for this heap ordered binary tree. Okay, now before we proceed, let me just tell you that if you know in the binary tree, if you know the index of a certain node, for example, this node here, if you know the index of that, how do you get the index of its two children, its left child and right child? So if this node has an index I, which is 3 in this case, what is the formula for the index of its left child? Well, it is going to be 2 times I. So this guy here is going to be 2I. And what is the index of this fellow here? It is 2I plus 1. All right. So if you know the index of any node in the binary tree, you can get in the heap ordered binary tree, you can figure out the indices of its two children as 2I and 2I plus 1, where I is the index of the parent. All right. So let's try that. If I is 4, what is the left child of that guy? Well, it is 2I with an index 8. And what is the right child? It is 2I plus 1 with the index 9. All right. Okay, so that's how you go from the index of a node to the indices of its two children. What about the other way around? Let's say you know the index of a node, call it I. What is the index of its parent? Well, the index of the parent is simply given by I integer division 2. All right, so it's integer division. So let me just put a floor here. All right, so this guy has an index of 9. What is 9 divided by 2? Integer division. Well, it's 4. Okay, the index of this fellow here is 11. What is 11 integer division 2? It's 5, and that's the index of its parent. Okay, so that's how you go from the index of a node to the indices of its children, and from the index of a node to the index of its parent. All right. And then also keep in mind that the indices here in the heap ordered binary tree have a direct correspondence to indices in the underlying array. Okay. Now, an important property to keep in mind is the height of a complete binary tree of size n is the floor of log n. Right? So if you have a binary tree such as this, which is complete, meaning it's fully packed, so you would have elements here and you have elements here. So that tree is now complete. And if it has n elements, then its height is the floor of log of n. All right. So in this case, how many elements do we have? We have 15 elements, and you take the log of 15. So here the height is the floor of log of 15 for this particular example. So keep that in mind. Now the other thing that we want to note here is that just like how we have a maximum oriented heap ordered binary tree, you can also define a minimum oriented heap ordered binary tree. All right. So here each node is going to have a key that is less than or equal to the keys of its children. Okay. So it's a similar definition. Now, going forward, we're going to refer to a maximum or a minimum oriented heap ordered binary tree as simply a heap. Okay, and we will be using a maximum oriented heap ordered binary tree or a maximum heap to implement the max PQ API, and we'll use a minimum heap to implement the min PQ API. All right, so that's what we're going to do. So now that we know what a heap is, let's talk about some algorithms on heaps. Right? And what we're going to do is we're going to focus on a maximum heap. Okay? And similar ideas apply to a minimum heap as well, but we will focus on maximum heaps. Okay? So let's consider the bottom-up reheapify or the swim operation or swim algorithm. Okay, so if for some reason the maximum oriented heap order, so remember what that is, that says that the key at a certain node, so this key 5 for example, is greater than or equal to the keys in the in its children, right? So this is 3, this is 2. So here there is no violation. This key is greater than or equal to the keys of its children. But what if this is violated for some reason? What if you instead of a 2 here you have a 7? That's clearly a violation. All right. So what do we do in that case? So if the maximum oriented heap order is violated because a node's key is larger than its parent's key, such as this case, then we can fix this violation simply by exchanging the node with its parent. All right, so we simply exchange these two guys. But when we exchange, that might result in a new violation with respect to its parent. All right, so what we do is we exchange the node with its parent and we repeat this until we reach a node with a larger key. All right, or we reach the root itself. So once you're at the root, there is nowhere to go. Okay, so let me repeat this. So if there is a violation because the node's key is larger than its parent's key, then what you do is you fix the violation by exchanging the node with its parent, and you repeat this until we reach a node with a larger key, or we simply reach the root. Okay, so that's how we fix this violation. And here is an example of this violation and how we fix it. So what we have here is a binary tree, but it is not quite maximum oriented. Why? Because look at this particular key T here. So T is larger than P. All right, so that's a violation. So how do we fix this? Well, we exchange T with P. So this T goes here and this P comes here. All right, but now notice that when you made that exchange, this results in a new violation because this T is again larger than this particular key. Right, so now we do one more exchange. So S is going to come here and this T is going to go there. Right, and now we are at the root, so we are done. And now notice that after these exchanges, the heap order has been restored. Okay? That's what you see here. So this is now a maximum heap. All right. Okay, so how do we implement this swim operation in code? Well, that's what is shown here. Okay, so we're saying we want to swim the key with index k. All right, so we want to have this particular key with index k swim upwards. So what's the code? Well, it's very simple. We say as long as k is greater than 1, meaning as long as we are not at the root, and if the key at index k over 2 is strictly less than k. Okay, so what does this condition mean? Well, we have to go back to what we said about an index of a parent relative to the index of a key, right? So if the index of a certain node is k, the index of its parent is k over 2. So what we are saying is here is that if the parent's key is less than the child's key, then it's a violation, right? So in that case, we simply exchange the keys, the two keys, right? The child with the parent. Okay, and then we traverse upwards. So we say that the new value for k is k divided by 2. Okay, so now you're at the level right above, and you repeat this for as long as k is greater than 1, meaning you're not at the root and you're looking at a parent that is smaller than the node itself. Okay, so that's the swim operation. And once you have the swim operation in place, the insert operation from the MaxPQ API can be implemented very nicely and efficiently. So the way you would implement the insert operation is you simply take the new key that you want inserted and just add it to the end of that underlying array. Okay, and since you're adding something to the priority queue, increment the size of the heap by 1, and then this key that you added to the priority queue might result in a violation, right? So you have to make sure that at the end the heap order is restored. So what you do is you simply have that key swim up, right, through the heap so as to restore the heap condition. Okay, and the way you have that key swim up is using this operation. Right? So let me repeat this. When you're inserting a new key into the priority queue, you simply add the new key at the end of the underlying array, increment the size of the heap by 1, and have that key swim up until the heap order is restored. Okay. Now, what is the running time of this insert operation? So think about it. So what did we say about the height of a binary tree, of a complete binary tree with n elements? Well, it is log n, right? So what is the cost of inserting a key into this heap? Well, it is simply the height of the tree, which is bounded by log n, because when an element swims up, it's basically traversing along the height of the tree, right? In the worst case, it's going to go all the way up to the root, but that height is bounded by log n. So the insert operation is extremely efficient. It's logarithmic. Okay. Now let's look at yet another algorithm on heap. This is called top-down reheapify, or the sync operation. So there is yet another violation that could result. So if the heap order, the maximum heap order, is violated because a node's key is smaller than one or both of its children's keys, so that's a violation, because you have something like this. You have a 3 here and a 1 here, but a 4 here. All right, so this is a violation because you're looking at a key which is larger than this guy, but it is smaller than this one. So that's a violation. And how do we fix this particular violation? Well, we use the sync operation. Okay? So if we fix the violation by simply exchanging the node, this node, with the larger of its two children. Okay, so what are its two children? It's 1 and 4. We exchange 3 with the larger of the two, which is 4. So 4 comes here after the fix and 3 goes there. And once that is done, the heap order is restored. Okay, and we have to do this until we reach a node with both children smaller than or equal to the node itself, or we reach the very bottom, the leaves. So there is nowhere to go below that. All right, so let me repeat. Whenever you have a violation such as this, where the node's key is smaller than one or both of its children's keys, we fix the violation by exchanging the node with the larger of its two children, and we repeat this until we reach a node with both children smaller or equal, or we reach your very bottom, the leaves. Okay, and here is an example of this violation and how it's fixed. So look at this particular key here, H. All right, so here what we have is H is smaller than both of its children. Okay, so what do we do? We pick the larger of the two children, which is S, and we simply exchange H with S. So this S is going to come here and H is going to go there. All right, and now here we repeat the same. So H is right here. Look at its two children, N and G, and you pick the larger of the two, which is N. So you exchange H with N. So this H is going to go here, and this N is going to go there. And we are done because now we have reached the leaf nodes. Okay, and the heap order is restored. So now in this tree, if you focus on any particular key, you will notice that it is greater than or equal to the keys of the children. Right? Okay, so that's the sync operation, and here is how you would implement it in code. All right, so sync takes an argument which is the index of the key that you want to sync, and the code is rather simple. So what are we saying here? So as long as 2 times k is less than or equal to n, so remember that if k is the index of a node, 2 times k is the index of the left child. So we are saying if that index is still less than or equal to n, then we say j is 2 times k. So what is j? J is the left child. Right? And then here we check if j is strictly less than n, because if j is strictly less than n, then you can talk about an index j plus 1. All right? So what is j plus 1? Well, j plus 1 is the right child. All right? So if j is strictly less than n, here what we are saying is if the left child is strictly smaller than the right child, then increment j by 1. So once this increment is done, j now is the index of the right child. So what we are doing here is basically picking the larger of the two children. Okay, so if this condition is true, we increment j by 1, and if we are here, then we know that j is either the index of the left child or the right child. Okay, depending on which one is larger. Okay, so j is here basically the index of the larger of the two children of k. Okay, and then here, what are we saying? If we are saying that if uh, the key at k, the node's key, if it is not smaller than the the key at j, meaning the parent is greater than or equal to its children, then there is nothing to do. There is no violation. We simply break. Okay, but if this is true, then it means that the parent has a key that is smaller. Okay, then it's two children. So what do we do in that case? We simply exchange the parent's key at k, with the key at j. But what was the key at j? It was the larger of the two children. Okay, so we simply exchange the parent with the larger of the two children, and then we say the new value for k is simply the index of that larger child. Right, so we are traversing downwards. Okay, so we repeat this until 2 times k is less than or equal to n. Right, and once the method when the method returns, the heap is in heap order. Okay. All right. Now, once we have the sync operation in place, we can implement the remove the maximum operation fairly efficiently. Again, recall that the two fundamental operations in a priority queue, in a maximum priority queue, are the insert a key operation and remove the maximum operation, right? So we already talked about how you implement the insert operation efficiently. So now using the swim operation. Here we're going to talk about how you implement the remove the maximum operation efficiently using the sync operation, right? So what you do is you take the largest key off the top, right? Because we want to remove the maximum. And where do you find the maximum in a maximum heap? At the root. So take the largest key off the top and then put the item from the end of the heap at the top. Okay. So take whatever is at the end of the heap and put it at the top. And then since you're removing something from the heap, decrement the size of the heap by 1. Okay. Now this new item that you inserted at the top might result in violations. So what you do is you simply sync that item down through the heap with that key to restore the heap condition. All right. So for example, if we were to remove the maximum from this particular heap, well, you would take this out and return it to the caller, and then you would take the last item, the item at the end of the heap, which is G, and put it here. Okay, and then you would simply sync this guy down, right, until the heap order is restored. So that's how remove the maximum operation is implemented. So what is the running time here? So here again the running time is log n, because in the worst case this sync operation has to traverse this entire tree whose height is bounded by log n, because it's a binary tree. All right. So now let's talk about how we implement the MaxPQ API. All right. So that's what is shown here. So this implementation is called MaxPQ, and it is a generic data type. So it stores generic keys, so objects of any type, and then it's an iterable data structure. So it implements the iterable interface. Right? What do we have for instance variables? Well, we have a static array called PQ. That's the underlying array that's going to store the keys of the priority queue. We have an integer n to keep track of the size of the priority queue, or the number of items in the priority queue. And then there is also a comparator, right? So we're not going to look at this much in this implementation, but you can guess why we need this, right? Okay. And then here is the constructor that is given a certain capacity. So what this does is it builds an empty priority queue with that capacity. All right. So PQ is created as an array of size capacity plus 1 plus 1 because remember that we ignore the value at index 0, right? And then we set n to 0, meaning this is an empty priority queue. And here is the other constructor, max pq, with no arguments, and that simply makes a call to this constructor. So whenever you say this as a method call, you're talking about a constructor, you're calling a constructor, and in this case you're calling a constructor with one argument, which is precisely this guy. So what this constructor will do is it will set up the underlying array with a capacity of 2, right? Because this argument is 1, so capacity is 1, so this thing is going to have a size 2. Okay, so this constructor simply delegates to this constructor. All right, and then isEmpty is fairly straightforward. You simply compare n, the number of elements in the priority queue, with 0, and then size simply returns n. So these are all constant time operations. So everything from the constructor to size, they're all constant time operations. Now let's talk about the insert operation. So this is one of the two fundamental operations in a priority queue. So we are given a generic key x, and what do? We first check if there is room for that key or not. So we say if n is greater than or equal to pq.length minus 1, so this means there is no room for this new key, so we resize the underlying array by making a call to the private resize method, okay, giving it this as the new capacity. So we double the size of the array. Okay, and then we say insert the item x at the index plus n. So we first increment n by 1. So notice it's a pre-increment, and then we say at that index we store the key x. Right? So the very first time when you make a call to insert, notice that n was initialized to 0, and we don't want to store anything at 0. Okay, we want to start storing at the index 1. So this does the right thing. So plus n would increment n to 1, and at index 1 you store the very first key, right? And so on. Okay, and then the key that you insert into the priority queue might result in a violation. But how do we fix it? We simply call the private swim method, okay, on that key. So we have that key that we inserted swim upwards, right, until the heap order is restored. And what is the running time of this method here? Well, it's log n because of the swim operation, right? And here I must say that it is log n in the amortized sense, because every once in a while the resize operation kicks in, right, which is a linear time operation. What about max? Well, max is extremely straightforward. It's supposed to return the largest key in the heap. Where do we find the largest key? We find it at the root of the heap. And what's the root in the underlying array? Well, it's the very first element. So we simply return pq at 1. Of course, we first check if the queue is empty or not. If it is empty, we throw an exception. But if it is not empty, we simply return the item at the index 1, meaning the item at the root of the heap. Okay. What about the del max operation? So here again we first check if the queue is empty or not. If it is empty, we throw an exception. Otherwise, we save the key at the root, which is pq at 1, in a variable called max, which we eventually return, right? But before we return, what do? We simply exchange the key at the root, which is 1, with the key at n, right? So we take the last key in the heap and replace the root with that, and then we decrement n by 1 because we are doing a deletion, right? So n is decremented by 1, and then after this exchange we might have violations. So what we do is we simply sync the root, right, until the heap order is restored. Okay? And then we say p at n plus 1 is null. So that last element that was removed, we set it to null to avoid loitering. Right? So that's that. And then we check if n is greater than 0 and if n equals pq dot length minus 1 divided by 4. Okay, so if the number of elements is a quarter of the capacity of the array, we simply shrink the array. So this is something that we've seen before. Okay, so that's the del max operation, and this is also a logarithmic operation because of the sync call here, right? And again, it is logarithmic in the amortized sense because resize kicks in every once in a while. Okay, now how do we implement iterator? Well, it's straightforward. We simply return an object of type heap iterator, which is this guy, and heap iterator implements the iterator interface. And how do we implement the iterator interface here? Well, first of all, think about the ordering that we want. So this is a max PQ. So when we iterate over the elements of this priority queue, we want items to come out in descending order. Okay, so that's the ordering that we want. Okay, so here is how we implement it. We have an instance variable called copy, which is an object of type max PQ, which is the data type that we're currently looking at, right? So it's simply an object of type max PQ that stores generic keys, right? And then in the constructor of heap iterator, what we do is we check if that comparator instance is null. If so, we simply create an object of type max PQ using this constructor. All right, and for capacity, we simply specify the size of the priority queue. Okay? That's a call to the size method from the max PQ API. So that's if the comparator is null, if no comparator was explicitly specified. But if there was a comparator that was explicitly specified, comparator is not going to be null. In that case, we make a call to a different constructor that max PQ has that was not shown in the code here, but you can check that in the text. Okay, so max PQ has another constructor that takes a comparator object as an explicit argument. Okay. So if the comparator is not null, we create copy as an object of type max PQ using this particular constructor. Right? Okay, and then what we do is a very simple for loop. So I goes from 1 all the way up to n in increments of 1, and we simply copy or insert the items from the underlying array, so PQ at I, into copy using the insert method. All right. So what we are doing here is we are simply taking the keys from the array PQ and we are inserting it into a max PQ, okay, which is called copy. So copy is simply a priority queue that stores the elements of this array PQ. Okay. All right. And then how do we implement has next? Well, we simply check if copy is empty or not. If it is not empty, has next returns true and false otherwise. And what about the next method? Well, if there is no next, which we report an exception. Otherwise, we simply do a del max on copy and return that. Right? So notice that the very first call to next on an iterator will return the maximum element, and then the subsequent calls will return the elements in descending order. And that's basically the ordering that we want. Right? And a very important thing to notice is that this del max operation removes something from this copy, okay, of the underlying array PQ, whereas PQ itself is not altered. So that's very important to keep in mind. So whenever you implement an iterator, you're not supposed to modify the underlying data structure. Okay, so here it might seem like we are deleting something from the data structure, but no, that was deleted from the copy of elements from PQ. So PQ is not altered at all in the process. Okay, so that's how we implement the max PQ API. Okay, so the two fundamental operations that we used were the swim operation and the sync operation. Right? Okay, now what about the running time of these fundamental operations? Well, we already have some idea on what that is. So in an n key priority queue, meaning a priority queue having n keys, the heap algorithms require approximately log n comparisons for insert and approximately log n comparisons for remove the minimum or maximum. Okay, so these two fundamental operations, insert and remove the minimum or maximum, are logarithmic operations. Okay. Now, it is not difficult to modify our code to build heaps based on an array representation of complete heap ordered ternary trees. Okay, by ternary trees we mean a tree where each node has at most 3 children. Right? And then we can also generalize that idea further and talk about d-array heaps for any given d. So there, we can talk about a tree with each node having at most d children, right? So there are d children. So it's basically a generalization of the binary heap idea. Now, the priority queue contains objects that are created by clients, right? And it assumes that the client code doesn't go about changing the keys, all right? Because after the keys are inserted into the priority queue, if the client code goes about changing the keys, then that invalidates the heap order, all right? So what we need to make sure here is that the clients don't go about modifying the keys once they are inside of a priority queue. And the way you can ensure that is by making sure that the keys are immutable. All right. Now, in many applications, it makes sense to allow clients to refer to items that are already on the priority queue. All right, and this data type called an indexed min-pq allows that. Okay, so it allows clients to refer to items that are already on the priority queue. Okay, so let's look at the API for this data structure called indexed min-pq. So you can build an indexed min-pq object using this constructor that takes an argument max n. So that simply creates an empty indexed min-pq where the indices go from 0 all the way up to max n minus 1. All right. So each key in that you insert in the priority queue is associated with an index, and those indices take on values from 0 all the way up to max n minus 1. Okay, and then once you have an index min-pq object, you can insert an item into it using this method. That simply inserts item and associates it with the key k. So this is what we are talking about here. So we can refer to this item now using this particular index k. Right? And then you can change the item associated with index k using this method. All right, so let's say you have some index k referring to some item in the priority queue. You can change that item by making a call to this change method. So you can supply the same value for k but a different value for item, right? And then you can check if k is associated with any item in the priority queue using this method, right? And then you can delete k and the associated item using this delete method. And then you can get the index of the minimum item using this method, min index, okay? And so on. So this is a variant of the min-pq data structure that allows clients to refer to items that are already on the priority queue. Let's look at a client program where we make use of the index min pq data structure. So this client program is called multi-way, and what it implements is a multi-way merge. Okay. So before we look at the code, let me show you some input and output. So here I'm showing you the contents of three files, m1.txt, m2.txt, and m3.txt. And notice that the strings in each of the files are individually sorted. So this guy is all sorted, this guy is all sorted, and this guy is all sorted. And if we run multi-way merge, giving it these three files as arguments, what the program does is it prints the contents of the file in complete order. Okay, so it has basically merged these three files, and hence it's called a multi-way merge. So it simply merges the strings in the input files and puts them in complete order. So let's go through the code now. So the code has two methods, a merge method and a main method. So let's start at the main method. So we first get the number of command line arguments as capital N, and then we create an array called ins of in objects. Okay? Remember that in is a data type that lets you read from files. So we're simply creating an array ins of size n, and this array is an array of in objects. Okay, and each object in this array is going to be responsible for reading each file, each input file. Okay? And then what are we doing in this for loop? Well, we simply initialize this array. So we say in set I is a new in object which is responsible for reading the ith file. Right? So in z0 for this example is going to be responsible for reading m1.txt. Ins at 1 is going to be responsible for reading that, and then ins at 2 is going to be responsible for reading that file. Right? And once we have ins initialized, we simply make a call to this method merge, giving it that array as an argument. So now let's look at merge. So merge is what implements this multi-way merge using an index min pq. Okay, so we get an array of in objects, we get its size as capital N, and then we simply create an object pq of type indexed min pq, right, with capacity n. And this indexed min pq object stores strings. Okay. All right, and then what we do is we say for int I equals 0 all the way up to n in increments of 1, if the ith object in ins is not empty, meaning if the file that that corresponds to in set I is not empty, or it has more strings in it, then we simply read a string from that particular file in set I, and we insert it into the priority queue with index I. Okay, so that's what we're doing in this for loop. Okay, so initially, if you go back to this example, once this for loop is done, I, when it is 0, it's going to read this string and stick it into the priority queue with index 0, and then when I is 1, we're going to read this string and insert it into the priority queue with index 1, and then this guy here is going to be inserted into the priority queue with index 2. Okay, so that's what you get once this for loop is executed for this example. You have a priority queue with 3 elements, A, B, and A, with indices 0, 1, and 2. Okay, and then what we say here is that as long as the priority queue is not empty, just grab the minimum key. Okay, so when the priority queue has these 3 keys, A, B, and A, the minimum, which is A, is going to be returned by min pq, and that gets printed here. So that's how you see this output. Okay, and then you also do a del min on the priority queue. So that's going to remove that key, and it's going to return its index. Okay, remember this is an index min pq, so it's going to return the index of that key. Okay, so that's I. And now we simply go to the ith input stream and check if it is not empty. If it is not empty, we grab a string from that particular stream and insert it with the index I. Alright? Okay. And you keep doing this until the priority queue is not empty, and once the while loop is done, meaning when the priority queue is empty, you simply print a new line character. Alright? Okay. And that has the effect of merging all these strings from the different input files into an ordered output. Right? So that's a nice client program that shows how you work with an indexed min PQ data structure. Okay, so now what we can do is we can use min PQ to implement a sorting algorithm. All right, and the idea is very simple. What you do is you take the items that you want sorted and simply insert them into a min PQ. All right, and then repeatedly remove the minimum and print it out. So when you do that, you're going to get the elements out in sorted order. Right? So let me repeat. So you have a collection of items that you want sorted. So you simply insert all the items in that collection into a min PQ, and then repeatedly remove the minimum. So the very first time you remove the minimum, you get the absolute minimum, and then the next time you remove something, you get the second smallest element, and so on and so on. Okay, so when you repeatedly remove the minimum from the priority queue, you're getting the elements in the sorted order. Okay, so that's how you would implement a sorting algorithm called Heapsort using a minimum priority queue. But let's talk about this in some detail and how you actually implement it. So in order to sort in place, what we do is we take our collection A that we want sorted containing n items and we heapify it. Okay, so we heapify that array A into a maximum oriented heap ordered binary tree. Okay, so we take that collection A and we turn it into a max PQ. Right, and then this is what we do. We repeatedly exchange the maximum key. So once the first step is done, you have a max PQ, so something like that. So the element that sits here is the largest element because it's a maximum PQ, right? So what we do is we repeatedly exchange the maximum key, meaning this guy, with the key at index n. So this is the key at index n. So we simply exchange these two guys. So whatever is here, which is the largest element, comes here, and this guy goes here. So now the thing to keep in mind is that this is the largest key. Okay, and then what we do is since we grab something from here and put it here, that's going to result in violations. So we reheapify, but we reheapify only the first n-1 keys. Okay, so we don't consider this this key here when you reheapify, right? We only consider the n-1 keys, which is all of these guys. Okay, so the largest key is now going to be fixed at that location. All right. But then, where is this key, this largest key in the underlying array? Well, the underlying array A looks like this. So 0, 1, 2, and so on, all the way up to n. So this guy here, the largest key, sits right there. So the largest key sits right there. Okay. So that's not going to move. That's going to remain fixed, right? So we simply reheapify considering the first n-1 elements, right? And when you repeat this once more, what you have here at index n minus 1 is the second largest element, and so on and so on and so on. And once this process is done, this underlying array is completely sorted in ascending order. Okay, so that's how we are going to implement heap sort. Okay, so this program is called heap. There is the public sort method, which gets an array of comparables. We first get the length of that array as n, and then in this for loop, what we are doing is the first step of the algorithm. We are heapifying A containing n items to a maximum oriented heap ordered binary tree. So that's what this for loop does. Okay. And then in here, what we do is, as long as n is greater than 1, we simply exchange the root with n, and we decrement n after that. So notice the post decrement, right? So we exchange the root with the item at n and decrement n by 1. And then we make a call to sync, but we sync on the first n minus 1 keys. Okay, because this n is different from the input n, it's decremented by 1. All right, so this is this while loop is implements the second part. Repeatedly exchange the maximum key with the key at index n and reheapify the first n minus 1 keys. Okay, so once the while loop is done, A is completely ordered in place, right, in ascending order. And here is the sync method that we've seen before, but this is just slightly different in that it takes n as an argument. Okay, because each sync needs to just reheapify the first n minus 1 keys, right? So we simply supply n as an argument, right? And it's this sync that is called here with a value for n. Okay. But other than that, it's the same idea. It's the same implementation that we saw before. Okay. So what's the running time of Heapsort? Well, Heapsort uses approximately n log n comparisons and n log n exchanges. Okay, and that is very clear from how we stated the Heapsort algorithm here, right? So we are inserting n items into a priority queue, and each item has a cost, inserting each item has a cost of at most log n, okay, because of the heap algorithms, right? So the total cost is n log n. So n log n comparisons approximately and n log n exchanges. So Heapsort is also a linear rhythmic sorting algorithm, and hence it is optimal. Okay, so it's comparable to sorting algorithms such as merge sort and quick sort that we have seen before. Okay, all right, so that concludes our discussion of priority queues. Thank you for watching.